and the population standard deviation is known, we are going to assume that the population is normal, and we shall think we are doing distribution of means for normal population. So we shall call this one distribution of means for normal population. But when the sample size is less than 30, and let me just make sure that there are two, 1, 2, or AB. Okay. And we call this one A, B. When sample size is less than 30, and the B, population standard deviation is not known, I'm going to call it unknown. First of all, sample size is less than 30. Second of all, standard deviation is not known. The population standard deviation is not known. C, what you know, let me just write. So you know sample standard deviation. So sample standard deviation is known. Known. We say it is not non-normal. If right here, the distribution must be a simple random sample. Let me put it here. It has to be a simple random sample, SRS. Whenever you hear SRS in this unit, this section, it means simple random sample, that everyone is given equal opportunity to be selected. Everybody is given equal opportunity to be selected. Simple random sample, equally likely. Simple random sample, but equally likely. It also means that everybody is given equal opportunity to be selected. Okay, so in a normal population, sample size is greater than 30. Population standard deviation is known, and it's a simple random sample. Okay, in other words, the sample is not a biased sample. The sample is not just a bias anyway. Okay, let's talk about situations where we have already talked about it. The left-hand side is when sample size is less than 30 and the population standard deviation is unknown, which means you are only given a sample. And if you're given a sample, you know sample standard deviation. Even if you don't know the sample standard deviation, you can calculate it. So if you're given a sample and population standard deviation is unknown, you already know is a simple random sample. Okay, now, what do we call the non-normal population? When we say that a distribution is non-normal, we shall say, we call this one T distribution, T distribution. Whenever the sample size is less than 30 and population standard deviation is unknown, we say it is a T distribution, T distribution. When the sample size is greater than 30 and population standard deviation is known, we say that this is a normal distribution, normal population, normal. You can still be told to calculate normal population. So now at least you know that there are conditions for normal population. There are conditions for T distribution. By the end of the day, even if we may not be able to read the chart for T today, but there is something called T distribution. So normal distribution, T distribution, So so actually there could be up to 5 distributions in this unit, but t-distribution is always used when the sample size is less than 30 and population standard deviation is unknown. So when we're looking ahead right now, looking at something like this is X bar. We called it X bar. So X bar is the sample mean. They are random variables. Since their values, they have random variables because their values vary. The values of X bar vary. For example, if I have a sample of 100, the big sample is 100. Well, what if I start taking samples of size 3? Okay, let me just say 5. Suppose I start taking small samples of small sample and the size is 3. Another small sample 2 of size 3. Another small sample 3. And the size is 3 again. And a small sample of, so what I'm trying to say that small sample 1, 2, taking different small samples, you find out that their means will be different. So in other words, X bar 1 is going to be different. It doesn't really matter what it is. X bar 1 will be different from X bar 2. So X bar 1 is not going to be equal to X bar 2. Neither X bar 2 will be equal to X bar 3. In other words, the mean of the first sample will not be equal to the mean of the second sample. We're going to come into do something like that. And the mean of the third sample will not be equal to the mean of the fourth sample. That's why we say it's a random variable. It's random variable because the means are different. Even though you're taking samples from the same population of 100, you're taking different samples of them, those means are going to be different. So what I'm going to do now is insert. Let me insert to the slides. So what I'm going to do is insert or get my, I'm going to get my whiteboard. I'm trying to make sure you know what I mean by taking small samples. Excuse me. And so I'm going to get a new whiteboard. There are no one. Okay, so let's first of all, I'm drawing some diagrams that are probably not in the book, but I try to make sure that you understand about drawing these diagrams. So the central limit theorem says, first of all, that if you have a sample that is skewed right, sample size of 100, but it's skewed right, and then you got another sample that is approximately normal, and you got another sample that is skewed left, all right. If the standard deviation of this sample, we can be given the standard deviation. Let's give the standard deviation, let's say, because it is not normal. Let's say that the standard deviation is, this is standard deviation of the sample. Let's say it is 10. Okay. Standard deviation 1, standard deviation 2 is, let's say it is 8. standard deviation 3, it is maybe 9. Okay. According to mean distribution, if you take small samples of this one, let's call it A. If you take small samples of this, and small samples of 3 from this one, and make yourself a mean distribution, and I'm going to make 2 diagrams so you understand what I'm saying, hopefully. Make yourself a mean distribution. In other words, I'm drawing something like a histogram. I'm making a mean distribution. See, I got a big sample of 100, but I'm taking small samples, let's say of size 30, and then I made a mean distribution. And what do I mean by mean distribution? I mean that this distribution is made of X bars, X bar 1, X bar 2, X bar 3, X bar 4, X bar 5. And so this distribution is made up of all X bars. The central limit theorem says no matter how skewed the original data is, the mean distribution will be approximately normal. No matter how skewed the data is, even if it is skewed right, or skewed left, or normally distributed, so even if it is from A, or B, or C, it doesn't really matter which one you get. If you take small samples from each of these data, A, B, C, that their mean distribution will be approximately normal. The mean distribution will be approximately normal. Okay, and what's the summary? So this is the mean distribution. Mean distribution. A mean distribution is the distribution of means. Okay, so now let me just draw a normal curve without the histogram so you can see. Try and make it a little bit cleaner. I'm trying to draw a normal curve that contains only means. So X bar 1, X bar 2, X bar 3, X bar 4. So you see what is called mean distribution. Why is it called mean distribution? It's actually made with X bars. Small means. X bar 6, X bar 7, and so on. So it's a distribution of X bars. That's why I showed it's a distribution of X bars. Okay, conclusion. If you're to explain the mean distribution, you say that the mean, we can now say the mean of the original data, is equal to the mean of the mean distribution. I want you to note from now on, it doesn't look beautiful. This is how to write the mean of the mean distribution. The mean of the mean distribution has X bar with it. Okay, so one conclusion of central limit theorem is that the mean of the original data is equal to the mean of the mean distribution. Okay, so And then the standard deviation of the mean distribution. Let me just write it this way. The standard deviation of the mean distribution. I hope you see. Whenever from now on, if you see a standard deviation sign with X bar behind it, it is the standard deviation of the mean distribution. Standard deviation associated with the mean distribution. So the standard deviation of the mean distribution is equal to the standard deviation of the original data divided by square root of sample size. Divided by the square root of sample size. And what is the sample size? I'm just going to write n here. Okay. So I am quickly going to find, let me now summarize the diagrams here. So the mean of this original data is, the mean of the original data, we can say that this mean x mu here, the mu here is 50. And the mean here is, they don't have to be the same. And the mean here is, I'm just use illustration. The mean here is 45, and the mean here is 60. Okay, so what is the standard error associated with data from here? Okay, so standard deviation is associated with this. And by the way, it's called standard error. The name is no longer, if you're talking about standard deviation, the standard deviation of a mean distribution is called standard error. Standard error. Standard error. The standard deviation of a mean distribution is called standard error. Therefore, if you want to associate this with a mean, you must write mu x bar, and the standard deviation will be standard error. Anytime you are talking about the distribution of means, you must be using mean with sub mu x bar. It looks, sometimes it looks like tautology, but that's what it is. Okay. The standard error is associated with central limit theorem. The standard error is written sigma sub x if it is a normal distribution. If it is not a normal distribution, you will see standard deviation of a small sample of a t distribution with sub x bar. So whenever you see standard deviation sub x bar and it's a sample standard deviation, oh, now you know that is a t distribution question. So how do you identify t distribution questions? You are given a sample size less than 30, or the standard population standard deviation is unknown. It could be both. Standard deviation could be less than 30. I mean, a standard deviation may not be known, and sample size may be actually greater than 30. It could be 1,000 sample size. But anytime you don't know population standard deviation, it is t-distribution. Let's get to the question. So because if you don't answer a question, these things may look ugly. Okay, let's answer a question. And we're going to a practice test right now. So answer a question. I'm putting a practice test down so we can answer a question. By the time we finish answering a question, it will be much, much better. We can start with question number 1. Good. Question number 1. Question number 1 is a good question. Already you see that squiggle X bar. You'll be asking yourself, what in the world does that mean? First of all, students get confused by looking at, it's a mean, population mean, and then X bar. We said at the beginning that mu is parameter and X bar is statistics. Why are they confusing us? I just want you to know it's not a mistake. It just means that this mean is the mean of central limit theorem. It's signifying mean of central limit theorem. So I already explained this question. It's asking you if the normal population has a mean of 79. That's what it's asking. It's an easy question, by the way. If the normal population is 79 and the standard deviation of a normal population is 28 and the sample size of that normal population is 49, find the mean of the central limit theorem. I'm going to say it again. This question is asking you to find the mean. Find the mean of central limit theorem. Of course, whenever you see this this written, it means the mean of central limit theorem. And because population standard deviation is given to you, it means that it's a normal population. Of course, you see sample size is greater than 30. So it's a normal population. And you are still told to find the mean of the, okay, so I'm going to draw a diagram. I'm going to draw a diagram. After some time, I will not be putting all this. You will not see this diagram in your book. I just use it for illustration. I use this diagram for illustration. It's not, I don't think it's in any book, but it makes, hopefully, it helps with understanding of central limit theorem. So when I have this distribution filled with X bars, then it means a distribution made with X bars. The mean of this distribution made with X bars should be written as mu X bar. Should be written as mu X bar. And mu X bar is equal to the mean of the original data. Mu X bar, we have already said that, is equal to the mean of the original data. Therefore, mu X bar is equal to 79. Because the theorem has already told me that mu X bar is equal to the mean of the original delta, so I shouldn't worry. Okay, so whenever you're given this question, you will have it from now on. Yeah, I'm going to have it a lot of times. If you don't know this, you won't be able to do confidence interval, which we have in chapter, the next unit 4. So you must know this before we continue. All right, so the mu X bar, because the distribution is made of sample means, the mu X bar is equal to the mean of the original data. And the standard deviation of central limit theorem is equal to the standard deviation of the original data divided by square root of sample size. And am I given the standard deviation of the original data? Yes. I am given that the standard deviation of original data is 28, right here. And I'm given that the sample size of that original data is 49. 49. So I can now find the standard error. So what is the standard error? I'll start with the denominator. Square root of 49 is 7. 28 divided by 7 is 4. Therefore, standard error for number 1, I'm going to write it here. Standard error is 4. So I've answered the question. We have answered the question. The standard error is 4. The mean of central limit theorem is the same as the mean of the original data. It does not matter how the person changes the question so it will look ugly. Central limit theorem says the same thing. It says that the mean of the original data is equal to the mean of the central limit theorem, or mean of the mean distribution. Okay, we answered question number 1. Okay, I'm going to ask you, is there any question? This is called central limit theorem. If you can answer this one, then you can answer other questions. Very soon we shall use a calculator because we shall do some other ones that are more difficult than this. But we have to understand this one. This is the basic. This is the basic, and we have ample time. So I'm not going to be in a hurry because this is the last section of Unit 3. So I'm going to take time to make sure that what I'm saying sinks. If you pay attention, it's not even bad. It's not even difficult. All right. Okay, so we have answered the first question. They already said the central limit theorem says a distribution may be skewed left or skewed right. It might be skewed right or skewed left or approximately normal. The important thing is that if you select small samples from the skewed left distribution, the distribution of those small samples will be normally distributed, whether you selected them from the skewed right or skewed distribution or normal distribution. And the distribution, this is called central limit theorem. And so you know that distribution of means is also called central limit theorem. Let me write it here. Also called central limit theorem. Okay, so distribution of means and central limit theorem are the same. We just saw a kind of question they will ask us in central limit theorem. If you can answer this basic question, you can answer others. Okay, we're going to look for another one that looks like number 1. Before we start combining questions, we want to make sure that we understand, because it doesn't even take time. It's actually easy. The explanation is all I have just said. We don't even need more. Okay, we don't even need more. All right, so now that we have talked about central limit theorem, let me do some addition. So I'm going to grab this and move it. I'm going to move it. Grab this and move it up a little bit. So right now, since we have talked about central limit theorem, and the central limit theorem is the distribution of means. All right, so what I'm going to do now is let's redefine z-score. So then, if the distribution of means has a normal distribution, what is the z-score of distribution of means? Okay, I'm going to let me try and make 2 columns. I'm going to make 2 columns, 1 column at the right, 1 column at the left. Okay. So we shall call this one distribution of means. Distribution distribution of means. And we shall call this one ordinary normal distribution. Ordinary normal distribution. It can be standard ordinary distribution. Okay, so this is distribution of means, and this is ordinary normal distribution. Okay. Now, let me talk about z-score. Z-score of an ordinary normal distribution, we talked about it already, is value minus mean over standard deviation. The z-score of distribution of means. So you see that z-score x bar, whenever x bar is under z, then it is z-score of distribution of means. Therefore, z-score of distribution of means is value. But what does value mean? Value means one x bar, because now x bar is a random variable. Right now, x bar is a random variable. So value, which means one random x bar minus mean divided by standard error. So that is the z-score of distribution of means for normal population. Let me rewrite it so that it will, just remember that standard error is the same as standard deviation over square root of sample size. So I want you to know, so we can say Zx bar is equal to X bar, which is now a random variable, minus mean. Of course, the mean, it could be mean of a normal distribution or mean of central limit theorem. It doesn't matter, they're going to be equal anyway. I want to rewrite this one as standard deviation divided by square root of sample size. So you know that you can write it as A or B. You can write it, they are the same. A and B are the same. The only thing is that you put it, okay. All right, so we wrote this for normal distribution. Of course, you know, you can see I'm using sigma, so it is normal population, normal distribution. But what if the population is not normal? What if the sample size is less than 30 and or population standard deviation is not given? So I'm just giving a raw data. Then it can be a t distribution, a small sample. If it is a small sample that has sample size less than 30 and the population standard deviation is unknown, then we call it a t. So we're just going to get into tx bar. Tx bar, I'm just going to get into that. Tx bar, normal distribution and t distribution, they look alike. They didn't provide any place for us to teach it except to use it. So we're going to be using it the way. So it is random, value minus mean. So I'm just going to say it is, because it has to be normally distributed, we're going to use mean over standard error. But the standard error right here is going to be S sub X. What is the difference? The difference is you are using sample standard deviation because the population is non-normal. In other words, sample size is given to you, probably is less than 30, and population standard deviation is unknown. It's a non-normal population, but you can still use it because if it is from a simple random sample. If you find out that the data does not have any outlier, then you can use it. Okay, so this is the z-score of a t-distribution. You can rewrite it as tx bar is equal to x bar minus mean over standard. Of course, this is standard error, but this standard error can be written as standard deviation over square root of sample size. It's the same. So standard error for t is the same. So now we have written what can happen in a non-normal situation. If this data is, if the data is non-normal, for example, that the standard deviation, the population standard deviation is unknown, or sample size is less than 30, we call it non-normal. But well, we can still use we can still use confidence interval and hypothesis testing, even when we get to okay. Because if it's a small sample, you can still find out that if you do one variable stat, the mean and the median might be equal. They can still be approximately normal, even though that you don't know the population standard deviation. And by the way, you don't always know the population mean. So when you don't know the population mean, you're going to be using sample mean. If you don't know population mean, you'll be using sample mean. Sometimes we assume population mean. You don't always know the population standard deviation. For example, suppose we are told to find the average salary of all nurses in the whole world. How are you ever going to find that? We are just going to take a sample of the world and use the sample to make a generalization. When we take that sample, we are doing descriptive statistics. And then when we finish, we use a statistic and generalize into the whole world and say we are doing inference. And so unit 4, now we get into inference. So we shall be using statistics to infer into the population in unit 4. And when you get to doing your thesis, when you're a graduate from college or master's degree or PhD, they will ask you to do thesis. You'll be using real world as population. I mean, you'll be taking samples. You know, if you're told to find the average value of average salary of all nurses, guess what? There's no way you can find the exact one. So you're going to take a sample. And when you finish with a sample, you convince whoever sent you that you're using a simple random sample, equally likely. And therefore, you can infer from your descriptive statistics to say the whole world. I mean, you can say summarize the average salary of the whole nurses in the world. And when you're doing that, you say you're doing inferential statistics. And that's what we're going to do in unit 4. And we are developing that from now. We're starting to say it now. We're starting to say the things we're going to use in unit 4 when we finish our central limit theorem. So whatever language we're speaking now, make sure you know it, because guess what? It translates to unit 4. No matter how hard it is, you must try to read up, do whatever you have to do, watch the videos, do any extra work to understand it. It's not enough to say I don't like it. It is so, I mean, the liking doesn't matter. You have to know it, because really, this is the beginning of inferential statistics. That's the beginning. So for any question, we're going to answer another. We are going to quickly go back and answer questions. So, by the way, we can now, very soon, we shall be given a normal curve. And this normal curve is going to be a normal curve containing random variables called x bars, and then you'll be given the mean of the normal curve, and then you'll be given standard error. Or you may not be given the standard error. They can give you the mean of the original data and standard deviation of the original data, and they want you to find the standard deviation. And by the way, they can ask you also to find the area under the mean distribution. If you're told to find the area under the mean distribution, well, remember that the mean distribution is still a normal curve. So you can still not use normal CDF, normal cumulative density function. You can still use it. And the same argument, but let me show you what is going to change. Lower bound, upper bound. Now watch it, mu x bar and standard error, standard deviation x bar. So from now on, we shall be told to find the area under central limit theorem. And we will be expected to identify that question as a central limit theorem question and use the formula as necessary. Okay, so let's get one and start doing it. And we will read the question and we shall know that what they're asking us. When we see it, we will know it. If you've been paying attention, when we see it, you will know it. Okay, let's go. Let's go to get a practice question that looks like that. All right. Okay, let's start answering questions and see what. Let's look at question number 4. First of all, you already see that this one has a mu sub x bar. Whenever you see mu sub x bar, that question is talking about central limit theorem. Do not mistake it as an ordinary normal curve. You do not want to do that. If you said you made a mistake, okay, well, you did, but you failed it. So when you see mu sub x bar, it means find situation. This situation concerns central limit theorem or mean distribution. Okay, normal population, by the way. Okay, well, let's read the question number 4 and see what it's saying. Okay, see, this one has standard deviation sub x bar. That question is asking you about standard error. You better remember that standard error is equal to standard deviation of the original data divided by square root of sample size. Okay. All right. So let's start reading question number 4 and start figuring out what they're asking us. Consider a random variable x that is normally distributed. Complete parts A through D. This is a reading assessment question. Be certain of your answer because you only get one attempt on this question. Okay. If a random variable x is normally distributed, what will be the shape of the distribution of sample means? All right. So that's what I've been shouting. You see, sometimes whenever I'm teaching mean distribution, I don't know, for some reasons I raise my voice, but I'm sorry if I'm raising my voice. Because the reason is I don't want you to make the mistake some students make, especially those who don't start on time, those who don't pay attention until maybe a day to exam, they start reading. Now, you can see we have two different normal distributions. So whenever you're given a question, you must read meaning into that question. And no one is asking you about central limit theorem or asking you about ordinary normal distribution. Okay, so let's answer this question. Okay, it says if a random sample X bar is normally distributed, what will be the shape of the distribution of sample means? It will not be skewed right. Okay, it will be normal. Because we already said it will not be skewed left. It's going to be normal. The random sample X bar is normally distributed. What will be the shape of the distribution of means? The shape of the distribution of means will be approximately normal. You can say normal. Any question? Let's go to B. If the mean of a random sample of X is 55, draw a diagram. Draw a diagram. Whether the question is mean distribution or ordinary normal distribution, draw a diagram. So the mean is 55. So they're asking you if the mean of a random variable X is 55, what will be the mean of the sampling distribution of mean? They're asking you if this has mu 55, what will be the value of mu X bar? Can anybody tell me what the value of mu X bar will be? Anybody in class? What will be the value of mu X bar? The value of mu X bar will be 55 also. The mean of the original data is equal to the mean of the mean distribution. The mean of the original data is equal to the mean of the mean distribution. Simple question. They just want to know if you paid attention. All right. Okay. Now, let's go to C. As the sample size n increases, what happens to the standard error? See, usually, let me put my calculator up. Usually, I don't want to tell this time. Let's demonstrate this. If I demonstrate it, you will understand it. Let's demonstrate question number C. We know the formula for standard error. As the sample size increases, what happens to the standard error of the mean? Let's not just memorize this. So the standard error, X bar, is the standard deviation of the original data over the square root of sample size. So we are going to say that our standard deviation, let's make it 10 so that it will be easy. Let's make it 10. And the sample size is, let's say that sample size is large, it's 50. So sample size is 50. Let's manipulate sample size. So original sample size is 50. The question is asking us if the sample size increases. So let's increase sample size. So first of all, we want to use a calculator to find the standard error. So we're going to find the standard error. So the standard error is standard deviation of the original data, which is 10 divided by square root of sample size. We said that sample size is 50 divided by 50. And when I get an answer, so if I hit enter, I get an answer. So this is the sample size when the standard deviation is 50. Let's increase sample size to 60. I want us to know that the standard deviation is constant. We're not moving standard deviation. We are only manipulating sample size, increasing it. Let's see. So after we increase it, we decide what happens. Whenever we continuously increase the sample size in a mean distribution, what happens? We're going to take a decision. Okay, standard deviation is constant divided by square root of 60. So we're going to make the sample size 60 this time. And we want to know what kind of answer do we have? Hit enter. The standard error decrease is decreased from 1.414 to 1.291. Okay, well, let's actually make sample size. Let's increase it to 100. So standard deviation is constant. 10 divided by square root of 100. We already know what it's going to be, but anyway, let's continue dividing. Okay, square root of 100 is 10. 10 divided by 10 is 1. Well, therefore, we can now conclude as the sample size increases continuously in any sampling distribution, the standard error decreases. We can say that. You can do this for yourself if you don't remember, because you don't want to guess. And guessing is not going to help you. So the standard, we now know the answer. As the sample size increases, the standard error decreases. The standard error of the mean decreases. The standard error of the mean remains the same. No, it cannot be B. No, it's not B. The standard error of the mean increases. No, we did an experiment and the answer is A. A is correct. And if you do this experiment, you see that you will not forget it. As you see, square root of n is in the denominator. If you keep increasing the denominator, then the number in the numerator decreases. That's what it is. And then let's conclude this question. If the standard deviation of the random sample, random variable is x, is 15, and the random sample of size 21, n is 21, is obtained, what is the standard deviation of the sampling distribution? So the standard deviation of the sampling distribution, which is standard error, whenever they call it standard deviation of the sampling distribution, you know it's standard error. You just have to know that. And so you are told that the standard deviation of the original data is 15, so we write 15 here, divided by, and the random sample of size 21, sample size is 21. You see, this is actually, the sample size is less than 30. So when you start, if you're doing, we're not there yet, but when we start doing confidence interval, we know that this confidence interval is a t distribution. You have to know that before you start doing any inference. What kind of distribution am I doing? Is it a t or a z? You better know the conditions. Conditions say when it's a t, it's a small sample, and the standard deviation is unknown. Population standard deviation is unknown. It could be both anyway. Anyway, the important thing is for now, we are looking for standard error. So we're not. So I'm going to ask my calculator to complete this for me. I will clear. The standard deviation is 15. Sample size is 21. So square root of 21. Square root of 21. And now I will ask my calculator to give me the answer. Uh-oh, sorry. I didn't divide 15. divided by square root of 21. All right. Okay, I'm gonna hit enter. Now by the way, you see, whenever you calculate the standard error and it is greater than the standard deviation, somebody screwed up. The standard error must always be smaller than standard deviation. As per the error I had before, anytime you calculate the standard error and it is greater than the standard deviation of the original data, something is wrong. The standard error must be smaller than standard deviation, because you're dividing a number with a big, with something. If it is 15, it's 15 over 1. And so whenever you divide by square root of a number greater than 1, the answer will be smaller. But just know that ordinarily standard error is usually smaller. Okay, so my answer to how many decimal places, be careful to check the number of decimal places. Type an exact answer, use radicals as needed. Okay, I can leave my answer as 15 over square root of 21. It says, because I'm actually allowed to use radicals. Do you understand the question here? The question says, type an exact answer. So they did not want me to write decimals. So you got to be careful. This question is asking you for exact answer. Some students don't even read. Even if you made a mistake, please read your question, read back. And in this kind of test, you can have 10 questions. But see, I want you to see that this question, there are 4 subsections. So if you have 10 questions and each question has 4 subsections, guess what? You actually have 40 questions. You actually have 40 questions. Okay. So the standard error, according to what I am told to do, is 15 divided by square root of 21. I am told to write an exact answer. Exact. Using radicals as needed. You see, they did not tell me to round my answer to number of decimal places. So you have to be careful. You actually know this. This is a simple question. You don't want to miss it because you did not read between the lines. Any question? Any question? We still have about 15 minutes. Let's see if we can, this is what we can do. Okay. Let's see what we can do. So we are still working on central limit theorem. Central limit theorem. Okay. I want you to see question number 8. Without doing any computation, put the following in order from least to greatest. Okay, we are going to come to this later on. We are coming to this. Let me get a question where it is obvious that the question is asking me about area under. Oh, okay, I want you to see this. I want you to see this. Whenever the mean, ordinary mean, if you're told to find the mean of any data, you can have mu x. It is not the same as mu x bar. Please note, mu x and mu x bar are not the same. This mu x only told you to find the mean of the random variable, the mean of the data. It did not ask you to find the mean of the central limit theorem. So mu x, mu sub x, and mu sub x bar are not the same. Let me show you something else. You got to be careful in this section. Note that what is written here is standard deviation sub x, ordinary standard deviation. It is not the same from now on as standard error with x bar. Hello, are you there? You must know the difference. You don't even want to screw your confidence. I'm talking about unit 4 because this is the beginning of unit 4. Central limit theory. Don't want to screw anything up there. Don't want to screw anything up. You want to start now to make sure you know the nomenclature